This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Okay, so let's get started by briefly going through that mid-semester test, or the progress test, sorry. If you've got any general questions as we go through just about the understanding, then let's discuss them. Or if you want to talk about your individual one, we can deal with that after. So, question 1, which was asking about the intra-prediction tool in H264 or H265. What I was after there was this, if you remember, the intra-prediction tool was the one, there's a pen, yes. Which was the one that took account of directional correlation between blocks. So if we split our intra picture up into, Tristan, up into the blocks as usual. Oh, I can't see anything very well here. Chop our intra picture up into blocks, and if there happens to be some sort of feature that is represents some sort of a straight edge correlation in a particular direction, and that continues through here, then we send a little bit of side information, a bit like a motion vector, but I don't want to stress that too much because it can be confusing. It's certainly not between frames, it's only within a frame, to say that the correlation is in this particular direction, and therefore that gives us a default set of algorithms that tells us how to predict this pixel from the neighbouring ones around. So some people understood that that was what was involved. I don't think anyone actually mentioned the fact that there was this bit of side information to indicate which mode. I might be wrong, but anyway. But you didn't lose marks because of that. Okay, and so why is that different from earlier standards? Well, the earliest standards of video coding did essentially no prediction within the frame. There was only, if we had transformed all of these blocks into the DCT domain, into the frequency domain, then there was some prediction about the DC coefficient, and in a particular mode of H263 there was another one where we tried to predict the zero frequencies in a particular direction from neighbouring blocks. I think one person understood that this was what was intended and got some marks accordingly, because it wasn't, intra-prediction is not completely unambiguous. But what I was really after was the modern one, the H264, H265 one, that had 9 modes in one case and 35 modes, I think, in the other. And it was the directional correlation. Why does that, why it contributes to the savings? It's because instead of encoding each of these blocks independently, we take advantage of correlation from one to the other between neighbours and form a prediction. The prediction error is smaller than the original signal, and so we save coding bits. In part B, we were asked, is it most useful for I pictures, B pictures, or P pictures? And on the whole, I've got to say this wasn't handled all that well. The answer was that it's only intra pictures, because it's an intra coding method. If the blocks, the macro blocks, were encoded using in P pictures or B pictures, then the temporal prediction was used. There is no question of doing intra prediction, so it's only applicable in I pictures. And that's of course one of the reasons why it's so important, because I pictures take up a lot of bits, and so if we get some savings there, they're important. Question 2 was asking about the voiced and unvoiced segments. What I was after in part A was just the fact that those two different types of speech can be characterized by the fact that the voiced segments have periodicity, which is a consequence of the vocal cord vibration, and the unvoiced segments are dominated by this noise-like signal form, filtered but noise-like stimulation. And why is that categorization into voiced and unvoiced segments useful? It's because instead of trying to encode the speech waveform faithfully, we can synthesize the speech by modeling it as being composed of the voiced segments with a particular periodic stimulus, or the unvoiced segments with a noise-like stimulus with appropriate filtering. So it was the fact that we can try to synthesize the speech rather than try to reproduce the waveform that gives us the advantage, and that's why we go to all the trouble. Then question 3 was about the what we just talked about the week before, I think, in terms of disk access for media streaming, and comparing the FCFS and the scan or circular scan ways of scheduling jobs for disk retrieval. And we were looking at advantages and disadvantages of each. So the advantage of the first come first serve system is that it is more likely to satisfy the requests in the timely fashion for the application, because the earlier they come in, the earlier they are processed. The disadvantage is, of course, that the data on the disk may not, and in general will not, be in the same order of the requests as they come in. So it means that the disk can spend a lot of time thrashing backwards and forwards, seeking to obtain new segments off the disk. So it can be inefficient in terms of disk usage. The advantage of the scan system is that it deliberately orders the requests in an order so that they can be processed in a single sweep across the disk surface, so minimizing those seek times. But the disadvantage is, of course, that we lose that sense of the order of urgency in those requests. So it might be that because they're scheduled later in the sequence, because of the location on the disk, we don't get them to the application in time, so we don't necessarily meet the deadlines. And finally, question 4 was asking about spectral band replication, what it is, why it's useful, and under what circumstances it's applied. So spectral band replication is that coding method applied to not speech. It's not a voice coding system. It's particularly applicable to music and wideband audio. And it's the technique where, in the circumstance that we're low on, well, our bit budget is running out, so we're trying to encode at quite a low rate, then rather than keep on introducing more distortion, we sacrifice the high frequencies. So we do a low-pass filter. We encode the low frequencies at reasonably high fidelity using almost any coder, and take advantage of the correlation between low frequency spectrum and high frequency spectrum, in particular things like the harmonics that continue out into the high frequencies, to describe the high frequencies in a parametric fashion rather than try to encode the high frequencies directly. Okay, so any questions? No? Excellent. You do have one question, yep. Is it specific to your paper, or we'll talk after?
Just to calculate the amount, it seems to be...
I can't add up, that's what you're saying? Okay, that's all right.
I need to know what's going on.
did-
Or X or...
Well, we'll talk in the break. Okay. So, let's start on the new topic for today, and we've turned a bit of a corner in that we won't be introducing that many new technologies and processes in the remaining lectures. We've only got 3 to go. This is our third last week, of course. But what I'd like to do is bring together those technologies that we've been talking about and discuss them in particular systems. And we'll start with probably the most important system that we have today and into the future will continue to be at least as important, and that's multimedia streaming over the internet, or OTT, internet delivery, where OTT means over the top. And we'll talk about what that means in just a second. Okay, so what is this OTT? Over the top, but over the top of what? It means over the top of a common independent network infrastructure. So, in other words, we're using the internet. Everyone can use the internet. There's no special capability to reserve resources. Everyone uses the best effort IP layer that's supported by the routers of the internet. So we can't do things like reserve resources and say, oh, I've got this video on demand service that I'm selling to these customers. I want to reserve the bandwidth. I want a guarantee of service, but rather we get the same network performance as any other service. So that's why it's called over the top. There's this independence of the network layer, speaking very generally, from the provider of the service. So Netflix, for instance, is mixed up with all the other HTML retrieval packets and everything else that's running on the internet. There's no reservation of resources, no private network just for that service, and delivery is subject to exactly the same uncertainty as everything else. All right, so it's a common term in telecommunications, over the top. So let's work through the contents list here and start by talking about streaming itself and understand exactly why streaming is an issue. So why make a fuss about streaming? Well, I'm sure, give it a couple of minutes to think about it, you would realise that that's where the challenges lie, because if we were just downloading and playing a video, then it would have nothing to do, or very little to do, with the network, in the sense that we would just have a file and we'd transfer it across from our server end or our encoding end to the decoder. Maybe there's a few exchanges in between. If there are packets lost, there might be some retransmission, whatever. We don't know at the far end. And we just download the entire file and then we start playing it out. But at the time we start playing it out, the whole of the network has no role. Right? We've downloaded a file. We do have to be careful of timing issues. We need to generate a video that's has the right frame rate, has the right audio pitch, all that sort of stuff. But it's all local. There are no delivery issues in the sense that this subject is called multimedia content delivery. It also has obvious disadvantages in that you have to download the entire file first, so there's a long delay before you can, or potentially a long delay before you can start playing something out. It's not applicable to live services, live events.
So it's not buffering here?
Sorry?
Isn't it buffering?
Well, it's not. It's buffering the entire file. Yeah. So, I mean, I really present that more as a contrast, as a baseline to refer something else to it. So what streaming is trying to do is transfer a little bit of the file, but buffer a minimal amount. So we only buffer as much as we need to ensure that we can start playing, and hopefully we have enough confidence that as we continue to play out of our little buffer there, that it will continue to be fed from the other side, and we won't actually empty it, as we've discussed. So not only is this a much more usable service, if you think of a video on demand service like Netflix, that you can start playing your video relatively soon after deciding on it, but it also throws up interesting technical challenges from the delivery point of view, because now we need to take account of timing issues right across that network, and we need to try to design our system such that we can have minimal response time, a very short response time. We need to ensure that we've got the throughput to satisfy this continual streaming requirement, and we need to consider how we cope with losses and errors. So the features of streaming services are that we aim to have immediate start and instant jumps. Of course, they're not truly immediate and truly instant, but they should be perceived by the user or the customer as being very short, almost like operating it from a local store. If changing video selection, we need a short channel change time. So imagine multiple live streamed events. If we switch between them, we don't want to have to wait a long buffering time between them. Because we're playing it out as we are receiving it, then there's no need to maintain a complete copy of the content at the client end. So why would that be good? A good thing a good feature. Sorry? Yeah, it increases security, so the content owners are happier, even if it's encrypted. You're obviously better off if there is not even a copy kept at the client, and also it can mean it's easier. Well, you don't run into problems of storage in the local device, so you don't have to be concerned about how much storage there is in a tablet, for instance. If it might be limited, and maybe you wouldn't have space for an entire, 4K movie. The fact that we can play out as we receive the content means it's suitable for live events and very long content. But from the technical point of view, what we need to worry about end-to-end error performance and need to consider, do we need a real-time protocol, or how are we otherwise going to handle those the timing requirements? So let's look at this issue of continuous throughput and consider what our challenges are here. Let's assume that we have a constant data rate or constant rate, say video service. Video means audio visual. We understand that by now. And just assume it's a constant data rate just so that we can easily visualize what's going on. Ideally, we'd like to see this sort of transmission over a packet network. So we have this constant data rate is supported by the network. We have fixed packet timing, so the interval between packets is fixed and reliable. And so these packets are arriving at this constant rate and reliably, and we can put them in this relatively small buffer here. And as we discussed previously, this decoder buffer only has to have enough data in it to satisfy the needs of the next frame that this decoder is going to request. So we have a minimal buffer, right? So a small buffer at the receiver collects just enough packets of video to ensure that there's enough to represent the next frame that it's about to render. But of course, IP networks aren't so perfect, and we have packet delay variation there, or jitter, because of the varying delays through the network. As I'm sure you're aware, different queues in the routers, different queue length in routers, sometimes a different actual route taken through the network as it responds to changing network conditions. And every now and again we might have this lost packet, and we need to figure out how we're going to deal with that. We talked about loss concealment and loss repair and all those sorts of things before, but we'll come back and we'll talk about that as well tonight. So this means we need, in addition to this decoder buffer, I'm making this logical distinction between these two, how they're actually managed. Could be the same block of memory, but there's a logical distinction between a transport buffer, which is there to accommodate the vagaries of the transport, and the decoder buffer. So the decoder buffer is the one that simply has to have the data for the next frame when that decoder wants it. It's the one that that MPEG virtual buffer verifier, VBV, yes, describes. So when we get information from the encoding end saying, I'm assuming you have at least 2 megabytes of buffer available and you shouldn't start reading out until it is this full, that's what this is referring to. It doesn't know anything about the transport system, the network. The transport buffer is here to make sure that we smooth out these packet delay variations, and it'll of course be dependent on the conditions of the network. And if it's big enough, if we want to take this path, then in the event of a packet loss, then maybe we're going to make that buffer so big that we have time to request retransmission and repair that that lost packet. We'll come to the practicality of that a little later. So we have to put a larger buffer in. So a larger buffer will avoid these problems of jitter. It may allow enough time for error correction, but that has some obvious consequences, right? The large buffer means long delays, means a slow start, right? We need to preload this buffer just the same as we have to preload the other buffers before we can start using it. If we suddenly decide to change streams, then we have to flush that buffer and again wait for it to part load before we can start playing out. And there's longer end-to-end delay, so that's certainly important for communicative services like FaceTime or Skype, right? So not looking good, but we'll pursue it. Interestingly, what it comes down to is a choice. We essentially have a choice between delay or continuous play. If we make these buffers very, very small, then there's the possibility of the buffers emptying and we have discontinuous play. We end up having to pause the play out and wait for more data to arrive. If we want continuous play, then we have to make these buffers larger and we suffer a consequent delay. So it's a trade-off between those two. We already have those buffers on the input and output of the, on the output of the encoder and the input of the decoder, as I've said, but now we're adding an extra layer, if you like, to accommodate the transport. So we might need buffers here to do the packetization, right? We need to accumulate enough bytes to fill up a packet. And if we're relying on the network transport for reliability, then we need to buffer data there because it might need to be retransmitted. And at the receiving end, as we've just discussed, we need to remove jitter and possibly request retransmission. Is delay really important? Well, people have done studies. This is a particular paper, not necessarily the only reference on this topic, but these authors did some studies of viewer behaviour in these circumstances where the retrieval of video in particular was delayed by various amounts. And essentially the conclusion was, and actually this is 2012, so the study was probably in 2011 or 2010, and expectations are probably raised, I would suggest, since then, 8 years ago, 9 years ago. But back then, the result they obtained was that after about 2 seconds delay, so I've selected my video clip of the cat doing something entertaining on the toilet or something, I don't know. And if it doesn't start within about 2 seconds, I start to think, no, I'll choose something else. Okay. So the abandonment rate increases from about 2 seconds, which does seem short, but you know, this is the result they obtained. And once these users have abandoned your site, gone somewhere else, they're less likely to return. And the acceptable delay depends on what sort of connection you're used to, not surprisingly. So if you look at the extremes there, people are accustomed to the delay that you experience on a mobile device, and so they're a bit more tolerant. It takes a longer delay before they start abandoning you. But if they're used to a highly responsive service on fibre, then they're much less tolerant of delay, and they start abandoning the site earlier. And it also depends on the piece of content. So I guess that's a kind of a psychological thing. If you're looking at a YouTube clip and it's only 2 minutes long, then you're only going to get 2 minutes entertainment out of it. So if it doesn't start very soon, then you think, oh, stuff it, I'll find another cat video. But if you're about to watch a 2-hour movie, then and it takes a little while to start, then you're prepared to wait a bit longer and invest a little bit more time for the entire 2-hour experience. Anyway, whether you believe the figures or whether those figures have changed over the time since, the conclusion is pretty clear that we need to try to achieve delay of the order of seconds, or people go elsewhere. They won't want to look at our site. And here are some network delay figures to just to try to provide a little bit of perspective there. The top set are they're just example rental lines, so they don't have routers, so it's not so they don't have queues. It's not an internet connection. It's a leased line. So we have tens of milliseconds up to around 100 milliseconds for international connections. But when we include the routers in an internet type connection, then we have the order of a few hundred milliseconds of delay. And that in itself is not large compared with the few seconds that we've just looked at, but it depends on how many round trip times we have before we can start displaying a video. So let's look at how we can manage try to minimize the delay that we experience. So, and to kind of illustrate this, I'll use this diagram which is trying to show both the amount of video that is received and the amount of video that's been played. If we look at our first reference kind of configuration where we download the entire file and then play it out, then we take some time. It's just modelling this as a continuous, constant rate download. And so after some certain time, we've downloaded the entire movie. That's what that's supposed to indicate. And then only at that point is the file available for play out, and we can play it out wherever we like. The advantage, of course, I didn't mention earlier, is that we can easily jump about wherever we like. But this does involve this long delay. So what determines these slopes, do you think? Let's start with this one. The bit rate, which bit rate though? No. It's the download speed, right? All we're doing is transferring a file. So if we can, so even if it's encoded at 4 megabits per second and we can download it at 10 megabits per second, then we'll download it at 10 megabits per second. It gets it there first. But here we're playing the file out. So this would be the 4 megabit per second version. This is the encoded rate. So there's no reason why those slopes need to be the same. In fact, we would hope that that one is at least as high as that one. Right? So if we look at that, we can see obviously why there's an opportunity to speed things up a bit. All of this content is in place in the receiver before we even start to play it out. So why don't we move that whole line earlier? And sorry. And so then we only have this short delay. As this continues to fill up our buffer at the decoder, we start to play it out, and as long as these lines are parallel or divergent, then we're okay. And so this is a very old version of YouTube, just to show the illustration, or just to illustrate the progress bars here, where we see the playout pointer and the download pointer. Right? These are managed a little bit differently today, which we'll talk later about that. So how the this progressive download, as it's called, is supposed to work is shown here, as we had earlier. We have a small amount buffered before we start playing out. This slope depends on the network resources. This slope depends on the encoded bit rate. But the problem comes is if the network supported rate drops during this the playout. And so we might have decided on the basis of the incoming bit rate and the playout rate of the movie or the video that after waiting this amount of time we can safely start, but the conditions could change. The network is variable, and they can intersect. And once they intersect, of course, this line is trying to play out something that isn't in the buffer yet, and so we have to pause playback and show that, or something like it, which we've all seen too often probably. Another problem with progressive download is that it can be wasteful if the playback is terminated early. So we can, even if the network is supporting the rate that we would want, we're accumulating more and more data here, and we're getting well ahead of ourselves here, but then we decide that that video of the cat wasn't all that interesting after all, and we abandon it. So if we terminate playback at this point, we've played out that amount, but we've downloaded that amount, and so there's all this wasted data. So it's not necessarily a good idea to get too far ahead of the playout rate, because often people do abandon the viewing. I haven't got any figures on that, but I think on YouTube it's very high. Okay, so how can we get around that? Well, there are fixes, though they're not necessarily very elegant. So, for instance, if we're using HTTP to download data as fast as we can from a server, so we've asked for a file, it starts to download it. It's would ordinarily be driven only by the throughput that it can achieve through the network. It doesn't even know what the playout bitrate of the video is. However, we can customize the HTTP behavior. So Microsoft, for instance, has this bitrate throttling approach where it initially sends a spike of data to preload the buffers, so we can start playing back as early as possible, which seems a good thing to do. But it's content aware. It looks inside the content and sees, oh, this is a movie and it's encoded at 4 megabits per second. So after I've initially sent this burst of data, I'll send it an average rate of, what is it? Well, it's 500 kilobits per second in this case. So that's maybe a bit of a solution to this problem of wasted network resources for video that's not viewed. But it does mean that we've lost the independence of the layers. Right? At this HTTP thing, it's not pure HTTP, it's customized, and it's not independent of the application. HTTP shouldn't know what it's carrying. It should just be bits. So now we have this interdependence between the layers, and why is that a bad thing? It means if the application changes, we've got to go and change HTTP, and that's the whole idea of the layering structure in the TCP/IP protocol stack is to try to keep all those layers independent. So this is the ideal that we're trying to strive for, really. True streaming, what you might call true streaming rather than progressive download, is where we can somehow try to match these streaming. Right? So the idea is that we have minimal buffering before we start to play out. So we only download a little bit before we start playing. And then we try to maintain the transfer rate at a slope, that is a bit rate, that is tracking, in some sense, the actual play-out rate. Right, so the slope of the play-out rate depends on the encoded video bit rate, and we try to match this the transfer rate to just keep ahead of the receiver. But of course, we can only do that if the network resources allow, and we always risk this situation in the event of congestion. So we again have to pause the play out and show our buffering sign again while we wait for more data to arrive. So how can we improve the user experience? Or sorry, that's wrong way to introduce this slide. So what we're looking at is an improvement in user experience throughout these through these three stages. So as a summary of the characteristics here are that the download and play approach is inconvenient. It's got this long delay before we can play back. We have these issues with storage of the whole file, whether there's space, whether there's a security risk, and it can't be used with very long programs or live continuous events. Progressive download improves the delay situation, but we still do have to wait some time before we can start playing out, because the algorithms have to have confidence that we'll be able to play out continuously all the way to the end. And it's uncontrolled in the sense that the download rate is completely independent of the play out rate. So it may work or it may not, we don't know. And it has this inefficiency if we terminate the playback earlier. We don't need to worry too much about this. I mean, early versions of HTTP weren't able to jump into the middle of the file. You had to just ask for the entire file. But now we can make byte range requests. We can say we want this byte to this byte, so that's not such a problem. True streaming is what we're ideally aiming for, in which we have essentially a TV-like experience. A short delay to start up and reliable play out. And highly responsive interaction, in the sense that if we pause, if we swap to another stream, then it happens almost instantaneously, fraction of a second sort of thing. But the challenge we face is that to achieve this, we need to minimise the buffering and the delays, despite this unreliable nature of the network connection. Right? Unreliable, not in the sense that it's designed badly, of course, just that it's best effort. And so there will be delay variations and there will be packet losses. So let's talk specifically about streaming over IP networks and the protocols that will support that. So have you all looked at TCP/IP protocols? Anyone not? Okay, so I'll just go fairly quickly over this just to make sure that we're not missing something, but you're familiar with their functions. Stop me if I go a bit fast though. So IP, at the IP layer, the network layer, we have this network, this datagram service. Every packet is considered a separate entity, so every time an IP packet gets to a router, the router says, oh, an IP packet, oh, it's got to go to where? And it makes a new routing decision on the basis of each packet. And as a result, the route could be different from one packet to the next. And at this IP layer, there's no reliability, there's no acknowledgements or retransmission. That's handled at another layer. There's no flow control, so the receiver can be overwhelmed with the the stream of data that's coming from the server over the network. There's no sequencing, so we don't know if the packets arrive out of order. And there's no congestion control in the event that the network becomes congested. And while we can detect errors in the packet header, the IP packet header, there's no check of any errors in the payload. Now TCP is ordinarily used on top of IP for many applications like mail and HTTP, so web surfing. And so we'll look at those characteristics to see their suitability from the media streaming point of view. So TCP operates on top of IP at the transport layer, so end to end, and it's a reliable protocol. So it adds the features that IP doesn't have for reliability. It adds sequence numbers. So it can tell when packets arrive out of order, and acknowledges the bytes that are received, so that we can tell whether they have arrived, and resend if the acknowledgements are not received or they're not as expected. And there's a checksum provided on both the header and the data at the transport layer, so we can detect errors if they occur. TCP also provides flow control, so the receiver can tell the sending end how much data it's willing to accept, or sorry, how much data the sender is allowed to send without getting any further permission. So that's a way for the receiver to slow down the sender. And there's a congestion control mechanism in that if packets are lost, then this the window size, this this chunk of or size of data, the number of bytes that are sent without acknowledgement, halves, and then builds up again while reception seems to be okay. And then if there's a lost packet again, it'll drop back. So as a result of those features, which are important to avoid network congestion, to avoid overwhelming the receiver, and to ensure reliability, really important for mail messages and HTML pages, there is substantial delay and there's substantial variation in the throughput, and that means it may not necessarily be well suited to media streaming. So TCP will correct lost packets. It'll retransmit lost packets. But we have, I'll keep coming back to the timing requirement that we have with audio and video data. So this is the ordinary sequence of events where, say, we're transferring an HTML file that we send a group of packets, we send off an acknowledgement, the acknowledgement is received at the sending end, and so the next group of packets are sent off. Somewhere there could be a packet lost, in which case the acknowledgement is either not received back here, or it's duplicated. I'll come to the duplicate acknowledgements in a minute to see if anyone would like me to explain. But in any case, we detect from these acknowledgements that something went wrong, and so we resend a packet. All very good if we want to ensure a reliable transfer of our HTML page. But the problem is that that retransmission involves significant variable delays. And in the case of streaming media, audio and video, we have particular clock marks in this timeline at the receiver in which we're expecting to be able to decode and display the next frame. Right? So if the packets are available, then the decoder can use them, but if there's this long delay because we need to retransmit something, then we risk the situation that the packets are not available when they're required, and so we end up back in that buffering scenario. Okay, so now I've got a little animation here which will take a minute or two to go through to just describe how the sequence number and acknowledgement numbers work and how we get these duplicate acknowledgements. Is it worth going through, or are you all kind of familiar with all that? Sorry? Go through it? Yeah? Okay. So it won't take too long, but I just thought it was worth including to make sure that we're familiar with the mechanism. So the exchange between sender and receiver to provide a reliability uses this sequence number and acknowledgement number. So the sequence number sent from the sender to the receiver is saying that I have sent you up to byte number 400 in this case. Right? It starts with a random number, but we don't need to worry about those details. So when the receiver sends an acknowledgement back, the receiver sends back a message that says, okay, I'm expecting now number 401, the next byte. So, and that's the acknowledgement number. So let's suppose that this sender has a file to convey to the receiver, and because of the selection of the initial sequence number as 400, then it's going to number the byte. We number bytes, not packets, in TCP. It's going to number the first byte as 401, as the receiver has indicated that's what it's expecting to receive. So let's just suppose, making up some random numbers, that that the first packet includes 200 bytes of data from this file. So the packet goes off to the receiver, and it goes with the sequence number 401. When the receiver receives that, it knows it can start creating a copy of the file. It numbers the bytes from 401, just as it expected. It knows it receives 200 bytes, so its acknowledgement that goes back to the sending end is going to be what? What's the acknowledgement number going to be? No, it indicates the byte number that it's expecting next. 601. Yeah, 601, right? So it's received 200 bytes, started at number 401, so it's now expecting 601, so that's the acknowledgement that it will send back. So at the sending end, we're now confident that those first 200 bytes were sent. We can now delete them from our buffer, at least at the TCP layer. We're not going to delete the file, of course. But at the TCP layer, we can move on. We've already sent those 200 bytes. So let's say that we now send 300 bytes. So the sequence number is going to be what? 601. Yeah, right. It's the byte number, the first byte, or the numbered byte at the start of the packet. So we send 300 bytes. Sequence number 601, received correctly, added to the file at the receiving end, and we send back acknowledgement number 901. That's right. Yeah. So all good. But so now let's say we send another 100 bytes. Again, a random number. You're understanding these sequence numbers and ACK numbers. So the sequence number will now be 901, just as the receiver was saying it's expecting. But let's suppose that packet gets lost. Okay. So now the subject to those constraints, or the possible constraint of the flow control, making sure that we don't overwhelm the receiver, the sender doesn't actually have to wait for every packet for an acknowledgement from every packet before it continues. If it did, it would severely impact on the throughput. Right? We would always have these long delays after sending one packet before we can send the next. And that would kill the throughput on the network. So we have a system with TCP whereby we are monitoring these acknowledgements, but we don't have to wait for every one. So having sent this packet, we can send another one. Having sent that one, we can send another one. So what's going to happen is that this packet never arrives at the receiver, so the receiver can't acknowledge anything. And so the receiver is just happily sitting there waiting for sequence number 901 to arrive. But the sender is just going to keep on sending for the moment, and it's going to send sequence number 1001, right, from its numbering, 100 bytes. And now things get a little bit interesting, because at the receiver end, we've received sequence number 1001. We were expecting 901. Okay? And so I don't want to get into the details. We have issues there, or questions there, about the different protocols, whether we save that data and try to fill in the gap, or we just discard this data. But anyway, we know that there's a gap there. And so at the receiving end, we acknowledge. And what do you think the acknowledgement is that comes back? 901, well done, that's right. So the receiver is sending a message back to the transmitter, or the sender, to say, hey, I don't care what you sent me, I'm waiting for 901. And so at the sending end, we have duplicate acknowledgements, right? And so that could alert the sender end to a problem. In fact, again, I don't want to get distracted to talk about TCP protocols, but that's not necessarily enough to indicate a problem, because if the packets were sent out of order because of a routing change halfway through, same thing would occur, right? If these arrived, if these were sent in this order but arrived in the reverse order, we would still have duplicate acts. So it might be that the sender waits for 3 duplicate acts, or even more, before it takes some action. And the action, of course, would be to resend this. So it wouldn't discard. Can't reach. Hang on a sec. The sender would not discard that chunk of data until it had been acknowledged. Right? So it's always sitting there. Anyway, that's to just explain how the sender can be aware that there are packets that have been lost, and how it can know when to transmit when to retransmit. And if you think about waiting 3 or 4 duplicate acknowledgements, that's quite a few round trip times that would be involved before the retransmission. So again, thinking, oh, this is a repeat slide, sorry, I didn't realise it was in twice. Maybe this is a bit more timely place to put it though, because if we think about an international connection and we have something of the order of 100 milliseconds one way, yes, one way, so 200 milliseconds round trip, and the occurrence of a bit of a lost packet could cause several round trips before finally retransmitting and moving on, then it's going to add considerably to that delay for the service. So, could we rely on TCP retransmission for a long-distance conversational service like VoIP, voice on IP? No, we couldn't, right? Because I can't bring up the slide immediately, but you'll remember way back in, I think, the first lecture, we talked about some service requirements, including the fact that conversational services become difficult once the round-trip delay is more than about 200 milliseconds, something like that, and that's comparable with around one round-trip time. So we're not going to be able to use retransmission for that. But what about video on demand? What do you think?
Maybe yes, because download and play.
Well, yeah. What about a Netflix service?
Netflix service. It's video on demand.
Yeah.
Netflix service. Because I mean, video on demand. It's like you have to download the file on like you have to download big file and then play it. So I mean, if you lose a packet, then you can use the packet available in the buffer and then send.
Right, but you need to have enough buffer during that time that you're waiting for a retransmitted packet. Your decoder is continuing to churn through to work through.
The file, the buffer.
Yeah, it depends on the buffer size. So that's why I was showing this diagram. Where was it? Here, to suggest that we probably need, if we're going to allow for those delays, multiple round-trip delays, to be able to retransmit that packet should it get lost, then that buffer has to be quite large, and that's potentially going to add significantly to the delay. It might mean several seconds, might mean, I don't know, 10 seconds, say, pick a number, after selecting your movie before it starts to play. But don't assume that's the end of the story, because we're going to look at alternative approaches that get around this problem. But from what we've described so far, that suggests that there would be an issue. So just keep that in mind. I don't want to take the time to look into this TCP sliding window. You're possibly familiar with this anyway. But basically, the idea is that we are able to send a certain amount of data without acknowledgement from the receiver, and that amount is limited by a few different things, including how much the receiver is willing to accept, the flow control thing, how much has already been acknowledged, and the degree to which there has been some congestion. Because if there's some congestion involved, then this window size will drop. And without taking the time to look through this, the consequence is here. The TCP/IP throughput, as a result of congestion avoidance, can look like this. It can have this sawtooth approach. So when a connection, a TCP connection first starts, it doesn't know how much throughput the network can cope with. Right? Later on, it can adapt when it detects that there are packet losses, but initially it has no idea. And so the algorithm that is used is called a slow start. So it doesn't look very slow because of the exponential growth, but this bit is quite slow. And it essentially sends one packet and waits for an acknowledgement. All good, sends 2 packets, waits for an acknowledgement. All good, sends 4 packets, keeps doubling, hence the exponential growth, until it's limited by something else, like one of these other windows, or if there are, it subjects the network to so much data that, along with all the other data it's handling, a packet loss occurs. And if a packet loss occurs, then we drop, we halve the window size, this congestion window size, and gradually increase it linearly this time. And then if there's more congestion, then we drop it again, gradually increase linearly. So admittedly, this is a worst case because there are other possible restrictions on the throughput. Could be the local network interface speed, for instance. You could be operating on a limited bit rate over your Ethernet or something, or it could be limited by the receiver. But if we're in the mode that we're limited by congestion, network congestion, then we could have this varying throughput, which is obviously not good for media. Okay. So we could experience this highly variable throughput. So we're talking about highly variable throughput. We're talking about highly variable delays, which isn't sounding good from the point of view of streaming media, in which we want short delay before we start up, and we want a reliable, high bit rate, high throughput support from our network. So it's a result of that kind of mismatch between what TCP offers and what media demands that led to the development of a set of protocols specifically for media. and they were based on the use of UDP. So the idea is that we can't afford the delays for retransmission, so we won't even try to detect them. We're just going to send out packets as soon as the data is available, and just send and hope. And if a packet is lost, then we just have to handle that somewhere else. That's the basic philosophy. So UDP, or some proprietary protocol, but UDP is the IETF standardized transport protocol, could be used instead. And UDP is a much simpler protocol, doesn't have any of the sequence numbering, acknowledgement numbering, flow control or congestion control. And doesn't provide any reliability. So packet losses might still occur. If they can occur in IP, they can occur in UDP. So the protection against the effects of packet loss have to be provided by some other mechanism, such as those we've talked about, right? If a packet loss occurs, then can we hide it? Or what can we do to recover as early as we can from that event? Brief word about UDP. I don't want to take the time to talk about the fields and the header and stuff, but it adds no reliability, no flow control, no error recovery. It essentially just takes the data in chunks and puts it into an IP packet and sends it off. Okay. So we're replacing TCP by UDP at the transport layer. So how do we operate a streaming service using UDP? Well, if we take a moment to think about what we're trying to do, we don't just have streaming media, but rather we have control as well, right? Because we need a connection to our server to be able to look through a database to find the service that or the video that we want, to make the selection, to maybe to pay for it, whatever, and perhaps even to monitor the connection once it's or monitor the stream once it's started. So there are actually two different streams or two different links that are involved. The streaming media, which is run over UDP, but the control stream, which is less sensitive to delay and more sensitive to error, and so we carry that over TCP. Right? So errors are a problem for streaming, but a non-zero error rate can be tolerated, and but we have these tight time constraints. So we put the streaming media over UDP IP, and the control of the media, selection, and so on, is something that can tolerate some timing delay, but we don't want to risk errors there, and so that's over TCP. So we have that sort of dual stack over there. So this isn't necessarily enough, really, to support media, just run it over UDP. The challenge we have is that we've got this unreliable, unpredictable UDP IP connection. And what we're trying to provide is some sort of robust, real-time media delivery service. So UDP doesn't provide that reliability, or doesn't provide any reliability or robustness. So the responsibility is pushed up to the next layer, or pushed up above UDP, and the result is a streaming protocol that's specifically designed to support real-time streaming. It's called RTP, Real-Time Transport Protocol. And what does it do on top of what UDP offers? Well, it doesn't do blind retransmission. So blind retransmission, meaning that TCP, when TCP retransmits something, it just retransmits anything that's missing. RTP has the potential to make some informed decisions. Is the retransmission still useful? And so I'm not going to retransmit something that can't be used. But a big role that RTP has is that it's aware of the data units that are being delivered. So it knows that there's where an audio frame is. It knows that there's a video collection of macro blocks, for instance. And so it tries to customize the packetization of this data in such a way that it is decodable independently of all the other packets. Right? Otherwise, we risk, if one packet is lost, one UDP packet is lost, then we not only lose all the data that's in that UDP packet, but that the last bits were the first part of some other macro block, and so the next frame is useless as well. Right? So RTP tries to delineate that the data that's in each of the UDP packets. But to do that, it has to be customized for the different media formats, right? It has to know that the payload type or the payload format is H.264 at a particular rate with particular options and so on.
But RTP was developed and is still used to provide this transport of for low delay streaming services. And RTP, I'm not a sort of network layer guru, but is generally considered to be still in the transport layer, but somewhat above UDP. Sorry. This is what RTP provides. It provides one session per media type, so we don't multiplex all the media together and put it over RTP, but rather we have one RTP connection for video, one RTP connection for audio, one RTP connection for the associated text if there is any, or an electronic whiteboard if you're in a conference situation, something like that. It provides the timing recovery to allow us to be able to indicate. It includes the clocks, the timestamps and clock synchronization data, so that we can synchronize clocks from one end to the other, and we can say that this piece of video needs to be played at this particular instant. And it does the sequencing so we can tell when data arrives out of order. It includes a field that describes the payload format, so that we have specific, we can map specific codec outputs to the RTP packets. So there's there's a separate RTP payload format that's defined for each codec, all in the IETF, RTF standards. RFCs. And as I mentioned before, the aim is for each packet to be independently decodable. And when we set up an RTP connection, we actually set up a pair of ports. So there's RTP, the real-time transport protocol for the actual streaming media, but there's that associated control channel that would be expected to run over TCP. And so we open one port for RTP, one port for RTP control protocol. So I've got a diagram coming, I think, of that. So this is just a packet capture screen that just shows the capture of a real-time transport protocol. So this is showing, are you familiar with this format? Have you seen this? This is Wireshark, or in the earlier version, Ethereal, it's the same thing. So these are all the packets that were on the network, and it includes this one. Between these source and destination IP addresses, Wireshark or Ethereal has interpreted it, and it's telling you that it's RTP inside. But the expansion is down here. So we've got the Ethernet frame, which carries the IP packet. The IP packet contains the UDP segment, and the UDP is carrying the RTP on top of it. And so what's included in the RTP protocol is version numbers and things, but it's telling us see if there's a timestamp here, and there's a sequence number here, and there's identifiers of the participants in the connection, and there's some payload type information here, which is telling us that it's audio, G.711, audio, PCM, A-law. So all that you need to be able to interpret that data. So the stream management thing with the dual stacks looks a bit like this. The media transport over RTP. Let me go back because I've confused things. This RTCP is not the stream control thing, despite the fact that it has control in the title. This is about feedback of the actual media stream. So it's providing data about the number of bytes sent, the jitter, real-time jitter, what the round-trip delay is, these sorts of things that can be used to, for instance, make decisions that at the sending end that maybe the network performance is dropping. Right? I'm starting to get increased numbers of lost packets. The round-trip delay is increasing. I'll switch to a lower bit rate of the stream. So this RTCP is also carried over UDP. It also has the real-time or short delay requirement. So that's why it looks like that. Sorry, I got a bit confused. So the media transport is handled by RTP and its associated RTCP. Sorry to throw all the acronyms at you. Between them, they look after delivery of the media, but also the packet sequence numbering and the delivery monitoring and so on. And the actual control of the media, that is selection of the clip and control of things like pausing and so on, is looked after over RTSP, thank you, over TCP. And so we end up with these dual connections. So an RTP session looks a little bit like this, or could look a little bit like this, where we have a few exchanges to request some media, to sort out options, to agree about capabilities, and set up the connection, request play, and then we have this time period in which the RTP audio and video are sent in separate connections. RTCP provides feedback about the status of the connection. We can pause in the middle, and at the end we just tear down the connection. So the bottom line, though, is to achieve what RTP provides, so greater robustness and reliability, we have had to make the streaming medium dependent, right? The server has to know about the contents of the packets, and so that means that there's an increased load on the server, right? It's the processor has to look inside the content, find out what the media format is, and where the boundaries of macro blocks are, and where the start codes are, all that sort of stuff. And we have to have a different flavour of RTP for every different media format. And indeed, if you search in the RFCs, you find that there are all these different definitions. So the payload type in particular is associated with RTP and tells it how to operate in each of those according to the different media. And every time there's a new media format, so H.265 for instance is finalised, then they have to go and write another version of RTP to accommodate. A technique that's intended to reduce the load on the server, though, was originally developed by Apple with QuickTime and has since been transferred into MP4 as part of that huge complex standard, and that's called hint tracks to assist with packetization. And this is trying to get around that problem of the server having to know about all these different media formats. So the idea is that that these hint tracks separate the different functions of encoding, packetization, and serving. So when we do the encoding, that's the time when we generate this hint track, and the hint track is provided and can tell the server which bytes to use in each UDP packet, or in each RTP packet, sorry, without the server having to know exactly what those bytes are. I'll show this in a graphic in a second. So the server doesn't need to analyse the media data in real time, but rather all it has to do is follow the hints, the instructions that are provided in this hint track. The server doesn't have to use it, but so it is able to generate RTP packets without it, but if it does use it, it just can take the load off. And this hint track could be stored with the media, it could be stored somewhere else, it doesn't matter. So what the hint track does is tells the server how to make the packets, it tells it how to create the right header, it tells it how much data to put in the packet and where to get that data. So the idea, the advantage of the hint track is shown by this comparison. So without the hint track, then a streaming server looks a bit like this, where the streaming server itself has to know about H.264 and MP2 and QuickTime and whatever other formats, and has to process each of those to generate the RTP packets and send the data off to a receiver. With the hint track approach, when you are encoding the data, that's the time that you generate the hint track and you send it along with the, or make it available with the media itself. And so the streaming server then doesn't have to know about all these guys. All it needs to know is how to process a hint track. And so it becomes independent of the media. So this is what the hint track will look like. So this, as the server works its way through this track, it comes across each of these blocks, and each block says, for this RTP packet, this is the header info you require. This is the information about what goes in the header, so the payload information, and then this is giving instructions about which bytes go into the packet. So then the server goes off to the media file, grabs that fragment, puts that in the payload of the RTP packet and sends it off, and then it goes and processes the next one. So as you see, this all needs to be media specific, or has to have been media specific to understand what all these segments of data are that go into the RTP packet. But the server itself doesn't have to. Okay, so we've been going for quite a while, so why don't we have our short break? But when we come back, we'll look at the exciting new development, relatively new anyway, in protocol terms. And that's that despite everything we said earlier, HTTP has indeed made a comeback in some applications at least. So if we can just take 5 minutes or so, have a short break, and then we'll just finish off till the end, and I promise I'll finish early. Yeah. That's a full. Okay, all right, I'll fix it. Sorry about that.
14 plus 6 to 19, right?
Yeah.
Yeah, and
I can't add up. Okay, all right, I'll fix it.
sorry.
No, my apologies. Okay. I'll bring it back to you.
Oh, okay. Also, can you explain this answer for me a little bit more? I'm not quite sure because I write down use for eye picture. This for sure. Right? So can you explain more why it's I didn't hear very clear. Just explain why it's more very useful for eye picture.
Because it's just because you've had this discussion about P&B, will save more bits
Only
only
by
by
prediction
prediction error
based
based
on.
on the eye picture.
So eye picture will save more bits on the prediction. Is that what you're trying to say?
But I mean, the P&B bits are not pictures are not relevant to this.
Oh,
at all.
okay. So what's the answer here should be?
It's useful for eye pictures because it reduces the bit rate or
The bit rate,
reduces
yeah.
the redundancy within a picture.
Within the picture.
Whereas
Yeah.
P&Bs are always predicted from
Okay.
others.
So if I write down eye picture will be saved more bits by the prediction error, something I will get a mark. Right?
Well, you got partial marks because you said this, right? So,
I mean, if I want to get more marks,
yeah.
if I write down
so
eye
if
picture,
if you'd said because it's intra-coding,
Yeah, intra-coding.
intra-coding applies
Yeah.
only to eye pictures.
yeah,
Yeah.
I get that because from that sentence, I mean, eye picture only doing this. Okay, I do it again. I didn't write down express well. Okay. Anyway, yeah,
Right.
it's fine.
Give me that. I'll fix it.
Okay, yeah.
Now we can start. All right. Let's continue on. I genuinely think we can finish a little bit early tonight. So let's try. So as I as I said, we're all excitingly looking forward to understanding how HTTP and TCP can have a role in streaming. So let's just step back and oh no, sorry, one other aspect of TCP I wanted to talk about. Sorry, it's the order might be a little bit odd, but there's another issue with RTP, which is how we decide what bitrate to send. Right? Because UDP will send whatever bitrate we give it. Okay? There's no flow control, no congestion control. So we can be as nasty as we want to our other people who are using the network. We just send whatever rate we can. As I said, TCP has this mechanism where it slowly ramps up the amount of data it's sending, if it's sending a large file, of course. And it will back off if it notices that there have been packet losses. No such mechanism exists in RTP because it's in UDP because it's a one-way process. So we need to decide how much data or at what bitrate we can send in RTP. And so how do we decide that? There are a couple of crude ways to do it, and one is what's called probing, which is nothing more sophisticated than just try it and see. So we select a bitrate, we try to send it, and we look at the RTCP feedback that will tell us that there are very long round trip delays, or that their packet loss rate is increasing, and as a result we might switch to another bitrate, or switch to another stream, or switch to another layer if we're using scalable coding. All of these things are possible. Another approach is that we can do what's called, we can model it. Modeling in the sense that we can do something that's considered to be TCP friendly. So TCP friendly in the sense that if we had a TCP connection, we would have about this amount of throughput, so let's send about the same rate. There are various models that are used to estimate the throughput of TCP, and this is one of them that I've pulled from this textbook here, and I'm not going to go into where that comes from, but just point out that it's maybe not very surprising that the throughput increases with the maximum transmission unit. So if you increase the size of the packet size, then we will increase the throughput, but the throughput reduces with a longer round trip time because of the time for acknowledgements and so on, and it reduces with an increased packet loss ratio. So actually it's the square root there, but so as we start to lose packets, our throughput reduces, so no surprise there. So we can, if we get some figures for these, then we can calculate what the throughput would be for TCP, and if we send about the same for our UDP connection, then maybe that's being friendly to the network. But there are limitations of these approaches, in particular this modelling one. Most obviously, if we're multicasting, then we can't do this because we have a different network conditions for our different receivers. Right? So there's a different round trip time to different receivers, and there's a different packet loss ratio for different receivers.
Is that rate for the connection?
No, sorry, it's not the it's not the interface rate. It's the rate that we send data over that interface. So we might have a 10 gigabit per second Ethernet connection, but we will only send a continuous 1 megabit per second, because if we go any higher, then the network further into the network,
Is it the link rate?
No, it's not the link rate. It's the rate that we put over the service rate that we put over that link. So just to say that there is this issue about deciding what rate we can send using RTP. So with all that background about network protocols and the need for short delay and the development of RTP over UDP and the development of RTCP and RTSP. It's time to just pause for a bit of reflection about where we are. So RTP UDP streaming gives us this low delay streaming protocol for media, which is certainly a useful thing to do. But while it tries to limit the damage from a lost packet, it doesn't actually solve the problem. Right? All it does is try to, as I say, it limits the damage. It tries to make each packet independently decodable, so that if a packet is lost, hopefully it doesn't affect the next one. But it doesn't actually provide true reliability. All it does is just push the problem up to a higher layer, so we might be able to do some concealment or somehow limit the damage in some sense. It doesn't provide true reliability. And you can also see that we're now forcing our servers, in the case of retrieval services, to become very highly specialized, right? So instead of just using off-the-shelf HTTP servers, we have to use servers that know about specific flavors of RTP. Hint tracks help in this respect, but they still have to be special hint track processors. And we need special proxies and caches that are to support these different flavors of RTP. And something we haven't actually talked about is that UDP can also be problematic for firewalls. Why is that? Well, because UDP is a one-way protocol. So, without getting too distracted into network security, I'm not an expert on network security anyway. The situation we have, if we say we have let's use a home network as an example, but it could be a corporate network, and you've got a NBN modem gateway or fiber gateway or something that's providing your connection into the network. Sorry, and it would have a firewall in there, and you've set up or you're talking to, let's say, the Netflix server over here. Or no, let's use YouTube, it's better. So you're talking to YouTube, and you've got this RTSP connection over TCP that you've set up from your computer, and it's talking to that remote server. It's two-way, it's over TCP, and the firewall was happy to allow you to make that connection, because when you first started it, when you first did the three-way handshake, I guess, with TCP, you sent out a request or a invitation to connect, and there was a response from the destination that you sent that message to. Yeah. So what the firewall does is check that something incoming is the result of something, is a response to something that was outgoing. So RTSP connection happens, works happily. Then you say, okay, that's the video I want. Stream it to me. And so then the YouTube server goes, decides on a port number from which it's this connection will include the port number to which this should be sent, but nevertheless this new stream comes to this firewall, which the firewall doesn't know anything about. Okay, so it's not in response to anything that's sent out there in the first place. And so the simple firewall at least will just block it, right? Will just stop it. A corporate firewall is quite likely to block it. And now you can, there are ways around this. We can get RTP aware firewalls that make the connection between what's happening here and what's happening there. But it's complicated, and we can face the situation where the UDP connection is simply blocked. So another problem for UDP and RTP. And let's suppose we want to adapt the content in terms of different rates, different qualities for different situations. We haven't talked extensively about this, but if we want to deliver the same content to a range of different devices over a range of different networks, so say I've got my YouTube video at high definition and I can play that out to a say a PC or a device that's going to show it on a big screen TV, but maybe I want to show the same content over a mobile connection to a small screen device. Maybe I don't want to provide that full high bitrate, or it's a different aspect ratio, or it's in a different coded format because the phone doesn't support the same media format. So to get around this, we need this facility, this content adaptation, and to achieve it, we need to know from the browser what device it is or what its capabilities are. Look it up on a database and send the appropriate version of the content. It might sound like it's not really necessary, but back in the day, back when I was working with Telstra, and they were trying to provide Big Pond TV services to a range of different mobile handsets. They were encoding something like 27, 28, 30 versions of exactly the same content in different formats at different resolutions with different parameters and different bit rates to satisfy that whole range of different devices. Which, maybe that's okay, but it means that another burden, if we're going to allow everything to be driven by the central database, is that it needs to decide which version to send. So at the same time as we have all these issues with RTP, UDP, modern high-speed switching is reducing delays, and errors are much less likely certainly on the backbone network, on the inter-exchange network. And as a result of this, there was increased interest in HTTP, TCP for on-demand streaming. I really need to emphasise the on-demand because we'll see how we can manage delay with the on-demand case. And this is why I asked the question earlier, and I said it's not so straightforward. But we still do need RTP, UDP, and we still definitely use it for conversational services. There's no way of avoiding that short delay requirement, and so FaceTime and Skype use RTP, UDP. But let's investigate this further to see how HTTP, TCP can be used for on-demand services. It's and the technology that's associated with it is called adaptive bitrate streaming. It has various names, but we'll use that one. So the idea behind this adaptive streaming is that, well, there are several concepts, but one is that we give streaming control to the client. So instead of the client negotiates with the server and says, this is the bitrate stream I want, and then the server just says, okay, I'm sending it to you, and here are the packets, just cope with it. But rather, it's the client that demands the particular chunk of the media. So the media is encoded into literally what are called chunks. It's a terminology that's used. So segments of, say, a few seconds long. And they're encoded at multiple bit rates. And it's the client that says, okay, send me chunk number 1 of the movie. And so the server just does what it's told and says, okay, here's that bit of that file, and then the client will decide when to ask for the next chunk of the movie, and so on. So the client manages its own buffer by by deciding when and how much additional data to request. And why is that good? It means that this server can be dumb. Right? It doesn't have to know about different flavors of RTP. It doesn't even have to generate RTP packets. It doesn't have to know how to interpret hint tracks. It just behaves like a conventional HTTP server. This client says, please give me this segment of this file, and it just grabs those bytes and sends them. Okay, so that means this server can be cheap, and it can also be fast because it doesn't have the processing overload. I've got some result that indicates that later on. So let's just pursue this a little bit longer. If we're going to give streaming control to the client. So what about this delay in this buffer? How are we going to handle that? We have this situation where we are feeding arriving packets into this buffer, and because it's a best effort network, every now and again we will lose a packet, and we said that we're going to have problems with this delay involved in asking for retransmission. And we get around that by building up a large buffer over time. So we start with a small buffer, and as we'll see, with a low bit rate. Right, so we're encoding the data at multiple bit rates. So we don't have to worry about the delay, because we can request a low bit rate. First few chunks of the movie, they arrive in the buffer and we start decoding and displaying it. And if we're lucky, we won't have any losses in that very early instant. But over time, we request higher bit rate, higher quality, and we build this buffer up, and so it is large. We don't know from the point of view of the user. When I first requested the movie, perhaps I'll keep on using the term movie because I need to emphasise that it is applicable for on-demand services. When I first requested the movie, I got a reasonably fast response, right? Because I was asking for a low rate version, so I was able to get several seconds of movie quite fast. So I was able to start decoding and displaying early. Then, as I've progressed, start watching through my movie, this buffer has been filling up to the point where it's storing about 30 seconds ahead of where I'm playing. Okay, so now I'm in exactly the ideal position that I want to be. Although, from the user's point of view, I've got a highly responsive service. I started it playing and now it's continued playing. And in the background, if a packet gets lost, I have the opportunity to request retransmission. Right, so I don't even have to worry about the error resiliency, the concealment and all that sort of stuff that we talked about, because we have a reliable communication or a reliable transport. And how big this buffer is managed by the client. So it's not the server doesn't even have to worry about it. Doesn't even have to think about it. So we still have some remaining problems though. We have these throughput variations that every now and again the network throughput might drop. We might not be able to sustain the high rate to keep that buffer full for 30 seconds worth of video. And although I've anticipated it from what I've just described, we need to figure out how we can do the startup quickly. But yes, so just a bit of a warning there, just to make sure that we understand that there are these two buffer functions, logical functions anyway, and this buffer that we're talking about here is all about transport. It's all about reliability and jitter removal, and shouldn't be confused with that decoder buffer that's managed by BBB buffer size and all that sort of stuff. So what's the adaptive part? When the network throughput drops, with conventional streaming, what we've been talking about to date, I suppose, let's just assume we're using constant bit rate, and we encode at this constant R bits per second. We can the logic works with the variable bitrate as well, but it's just simpler to visualize if we assume constant bitrate. So let's suppose we temporarily, because of network congestion, we can't sustain R bits per second throughput for, say, this T seconds. And we would have to pause. Right? There'd be no alternative. We just have to show that buffering message because we've run out of bits. We're expecting R bits in T seconds and they're just not arriving. We only have one bit rate from which to choose. So we just have to give this message. We have to pause our video and maybe give a message to say buffering, buffering, buffering. But if we just step back from our assumptions about how this is going to operate, let's think about what we would like to achieve. So if we change our requirement from we want to keep decoding and displaying video throughout those T seconds, we change our requirement to that. So instead of saying we need to acquire R bits in T seconds, what we want to say is instead that our objective is to keep decoding and displaying video throughout those T seconds. And so how do we do that if we can't get R bits per second through? Well, we deliver at a lower rate. So we deliver at a lower quality. That's why we have multiple bit rates. Yeah? So we might be able to deliver at this smaller rate for those for that time interval, and we accept this as our penalty. So instead of our penalty being a buffering delay, we reduce the quality temporarily, but at least we are able to keep playing. So we just have a different quality of service compromise. We're either pausing the video because we can't get enough a high enough bit rate through, or we temporarily reduce the quality because we can't get enough bit rate through.
So it's not going to be constant bit rate?
No, that's right. It's we're switching between, in what I've described here, it's a constant rate, but we have multiple encodings. So it's constant rate for each of those encodings.
Yeah,
And we're switching between them. Yeah.
Talk about the link.
Yeah, the link is supporting a different, a varying rate, or discrete rates. We're switching between discrete rates. Maybe that's a better way to describe it. But in fact, the same thing can be done with variable rate of different qualities. So for fast startup, how do we achieve that? With conventional streaming, we'd have to say that, let's say we decide we want at least one GOP, group of pictures of video, before we start decoding and displaying. So we can only get that if we wait one GOP of time to transmit it. Okay, or we might be able to send faster than real time to reduce that. But the problem we have with sending data early is that TCP slow start algorithm. I don't know how familiar you are with it. I've referred to it early, but if I go back to my diagram here, remember I mentioned that because at the very start of a TCP connection, and that's what we have when we first connect to a Netflix server, we've got to set up a new TCP connection. The TCP slow start algorithm ramps up its throughput. Remember, it sends one packet, waits for acknowledgement, sends two packets, waits for acknowledgement, sends three packets, sends four, and so on. So there are multiple round trip time delays. So even if the round trip time is only of the order of a few hundred milliseconds, we have a very small throughput initially, and we have multiple round trip times before we can build that up. So we do have this slow start. So we won't be able to commence immediately at that capital R bits per second or faster, but rather we'll have to be ramping up towards that. So we just redefine our objective. So instead of we decouple these two concepts. Instead of trying to get GOP time times R bits to the decoder, we just say we want to start playing the video in as early as we can, and we do that again by using this lower rate version. So again, the quality of the video at the lower rate is going to be less than that at the higher rate, but at least we start playing sooner. And in this case, the quality of service compromise is that instead of waiting longer to play at the target quality, we start playing out faster, but with a temporarily reduced quality. In fact, I don't know if any of you guys use Netflix. Have you ever noticed that? That the quality at the start can be lower, and it takes a few seconds to ramp up. And every now and again, while you're watching the video, it can reduce. It can become a bit blurry, a bit not really to the point of being blocky, but the resolution can drop. It can be a bit blurry for a little while, and that's because they're using exactly this algorithm. What happens for stream switching and channel changing? We do exactly the same thing. It's the same argument for the fast startup, that when we switch to another stream, we start at a lower bit rate. So we're adapting the selected bit rate to achieve this fast startup and switching, and we always try to maintain continuous playout. So graphically, let's look at what this means. If we have conventional single bitrate high quality streaming, then if the encoded media rate is shown by the green block, but the available rate varies because of network congestion, then there is no alternative but to pause every now and again while we wait. So we put this buffering message when our buffer is empty, and we have to wait for the available rate we have to wait to accumulate enough bits that we can start playing again. With adaptive streaming, the idea is that we start at a low rate, build up when we have confidence that the throughput seems to work, and when the throughput starts to decrease again, we switch down to a low rate version again. So the quality is going up and down over this time, but the objective is to continue playing, so we have this continuous play out. So we've traded time, the buffering delay, for the quality. So
Value with quality.
yeah, and so instead of having variable time, if you like, we've got variable quality. We have to lose something if the available rate from the network changes. But the aim here is to drop the quality for a bit rather than have to interrupt play out. And the same process occurs with the switching delays. If we had the conventional coding, then we are sending at this constant rate until we decide to switch to another video. So we switch stream, we would start downloading or transferring the new video at the new rate, but at that time we have to preload buffers again before we can start playing out. So what happens is that we've got the other buffering delays because the network throughput isn't all that good, but at this point we've got to buffer again because we've got to accumulate enough before we can start decoding. With the adaptive streaming, the idea is that we build up bitrate as we can. We adapt when the network throughput is reduced, and if we get to the stage of switching streams, then even though the throughput might be high enough, we switch to a low rate to start, and we build up again. So this means that we have, at the earliest possible time, we can start playing out. And so as a consequence, ideally at least, the aim is that we just switch rapidly to the next stream, and we are able to continue playing out. This is just a graphical way of illustrating what the adaptive streaming process is. It's a graphic comes from Microsoft. They provide one of several different solutions. And so they're contrasting here the traditional streaming with a single stream of data at a fixed bit rate, with this adaptive streaming where we have multiple rates available, represented by the different size cylinders, and we request a different chunk at each time, and we, if partway through the client decides it would be better off, for whatever reason, to switch to a lower, a smaller rate chunk, or a higher rate chunk, then it's under its control. There is a demo of what Microsoft's version of this is called Smooth Streaming. There is a demo here, but I can't show you because I can't install Silverlight on this device. So if you're interested and want to try to install Silverlight, you're welcome. It's quite good in that it has some sliders, so you can just adjust it's a simulation, of course. You can adjust what the network bitrate through is, and it just shows you how it adapts the bitrate and changes the quality accordingly. So the principles of this HTTP adaptive streaming, as it's also called, is that we strive to maintain quite a large buffer, as I said before, something of the order of 30 seconds is typical, and that allows TCP retransmission when packet loss occurs, and that's really valuable, right? Because we essentially have a fully reliable connection. We don't have packet losses. We don't have those odd blocks and persistent errors from one frame to another due to the predictive coding. Initially the buffer's empty, of course, but we grow it as fast as we can, and hope that we don't suffer losses in that early time period. And how do we handle all these different streams, though? Well, we have to provide details of what's available to the client, and that's provided in what's called a manifest. So that's the same term in shipping. A ship has a manifest which says what the cargo is, what's in all the containers or whatever. And it's the same concept, that this manifest provides the client with all the details about what streams are available, at what bit rate, in what format, and the client can make the decisions. So the client makes the decision about which piece of video or audio is requested and delivered, and the video and audio can indeed be selected independently, as we'll see in an example in a minute. And the client is the one that adapts by requesting lower bitrate versions as necessary to ensure that there's continuous play. And the client manages its own buffer at whatever level it wants. And the client also can decide not to request content too far in front of where it's playing, because of that issue of avoiding wastage. If we prematurely cease to play the video, then we don't waste too much downloaded data. And so you'll see, for instance,
How can we do that?
pardon?
How can we implement that? Request that.
Oh, well, with the client simply stops making requests, right? So the buffer fullness, or in fact, and you'll see this in YouTube these days, that you play a YouTube clip and you'll see the progress bar going a little bit ahead of your where you're playing.
But not too far.
But but if you pause it, it'll keep going a little bit, then it'll stop.
Oh, wow. But we are not doing anything, right?
Sorry?
We as a client not doing anything. It happens automatically.
No, the client is doing it. I'm not sure that YouTube is operating using adaptive streaming on every client. It depends on the client, but most clients, certainly on Chrome, for instance, it will be using adaptive streaming. So, unbeknownst to you, you don't actively have to do anything, of course. But sorry?
I thought we have to do anything.
Oh, no, sorry.
Select the quality.
No, you don't have to do anything. It's the algorithms in the background managing all this for you, and it will strive to get the highest bit rate it can, or maybe you make a selection these days about what quality you get. But built into that buffer management algorithm, or the client algorithm is a decision about how much in advance it will download, but then it'll stop and it just won't request any more until you start playing again. Okay, so where do these different versions of the content come from? Well, they could come from completely different encodings, or it could be a scalable representation, right? Now, this is not common, at least not common yet, but there's absolutely no reason why a switch to a different bitrate couldn't involve a selection of a different number of layers in a scalable representation. So the advantages are possibly already obvious, but when the link has varying throughput, the quality varies, but the play out continues. You might argue if you prefer the maximum, the highest quality, you prefer to wait for a while to make sure that it is always at high quality, but generally it's seen as advantageous to be able to provide that very quick response and a continuous play out rather than ever delaying for buffering. The intelligence is moved to the client, so this is always, as a rule of thumb, it's always a good thing to do, is to move intelligence away from the central point. So if we make the servers dumb and the caches dumb, then it makes them faster, it makes them cheaper, and there's always a lot of intelligence in client devices these days. There's lots of processing power, and so we can easily run the client there. And the server is simpler, so it doesn't have to even know about state information. It doesn't have to know how much data it's sent to you. It just responds to every individual request. So new request comes for chunk 59 from this movie, it just provides the bytes and doesn't even know that previously you chose chunk 58 or what bitrate you chose last time. It doesn't care. And so because the servers are simpler, and I mentioned this before, standard HTTP servers can be used instead of having specialized streaming servers. And this means that the servers are more scalable. So this is a result of one particular investigation of this point, where a comparison was made between the number of clients or the CPU load to satisfy a certain number of clients using just HTTP serving on a 4-processor PC server of some sort, 4-CPU server, in the case of HTTP or RTP. And as you see, as we increase the number of clients for RTP, the CPU load rises dramatically, so we can accommodate many more clients using HTTP. Of course, I haven't got all the details of the simulation, but the comparison is stark. And we don't have firewall problems with UDP that I mentioned can occur with UDP because everything's on TCP, so everything gets through. It obviously can't do multicasting, right? It's client-driven. Well, we'll talk about how we can simulate multicasting and broadcasting, but as I've described it, because it's client-driven, it's not a case of the server sending out one stream to multiple receivers because the receivers have to request them.
Simulcasting is the same thing? Multitasking and simulcasting is the same?
Well, simulcasting is sending the same version in different formats. So
It's like a scalar representation.
I think they're independent concepts, actually, because you could potentially simulcast an event in 2 different formats to just 2 different receivers. You're not necessarily sending to a large number. Anyway, maybe we'll come back to that one. So this adaptive bitrate streaming has had a number of names. It emerged actually around 2006. A particular US company called Move Networks, you've probably never heard of them, came up with it. And they were growing and growing, and then the big guys saw the potential and they moved in. And I think Microsoft bought moved networks, but they've essentially disappeared. But over the few years afterwards, so it's not actually a very new protocol. It's been going for about 10 years now. But all the major players, Adobe, Microsoft and Apple in particular, are using some version of adaptive streaming. Mentioned Widevine down here. It's not very well known, but it's been bought by Google and actually used to be used by Telstra. As far as I know, it's still used as well. And it has a version of adaptive streaming. They have different names: dynamic streaming, smooth streaming, HTTP live streaming, or HLS. But they do the same thing. But there are differences between them. It's worth highlighting the different approaches that were taken by Apple and Microsoft, not because there's, one's evil and one's good, but just that from a technical point of view, you can implement this thing in different ways. So Microsoft's approach was to use very short segments, 2-second video fragments. So a single group of pictures goes in each of these chunks, and all of these fragments were put in the same MP4 file, so a fragmented MP4 file, which is just a container file essentially. And in that same file at the start there's the manifest, so that describes everything that's available, the codecs, the bit rates, the resolutions and so on. And then the client, once it reads that manifest information, knows how to make HTTP GET requests to request segments out of the middle of that file. Apple took a completely different approach, at least early on. Now they've moved to a standard that we'll talk about in a second. So they were using MPEG-2 transport stream files, which we haven't talked about yet, but we will when we talk about digital TV, because that's used there. It's essentially just a way of chunking up data into fixed size packets, essentially. The fragments are longer, typically 10 seconds, and they're each in a separate file. So there are thousands of files stored away in these folders that need to be retrieved according to the manifest. So there's a separate file for the manifest as well. So it was quite a different approach, longer fragment time or chunk time, and a separate file for everything as opposed to everything in the same file. But more kind of historical interest because Apple's recently changed to a more common format. Because now there's a standard, of course, so who do you think managed the standard? Where do we go for standards for media? MPEG, of course. So the standard is called MPEG-dash, dash for dynamic adaptive streaming over HTTP. And this diagram just illustrates what's in the standard and what's outside the standard. The usual principles apply to standardization. We want to provide connectivity, but if it isn't an issue of compatibility or correct interpretation of data by the client from a server, then we don't need to standardize it. So Dash doesn't standardize the media player. It doesn't standardize how you decide at what point you stop requesting chunks of data because the playout has paused. Right? That's up to the client. It's not a matter of compatible protocols between a client and server, but it does define how you parse the MPD is what's the term? It's the term that Dash uses for the manifest. But oh yeah, thank you. Media presentation description. Yeah, that's the manifest. So we need to be able to parse that. We need to be able to understand that file to tell us what these segments of data are, and we need to parse those segments when they're brought down, and pass them on to the media player. So that's what's in the standard, and the format of the data in the server is standardised, but not things like the control systems, and the standard is essentially independent of the encoding as well. The idea is that it would be able to accommodate different types of encoder. So this illustrates how the data is structured in this MPD. So that we have periods of time that are defined. So in 60-second chunks in this case, and for each of those periods we have different adaptation sets. So one would be for audio, one would be for video, one would be for subtitle text or something like that. So every time as we work through this file at the client end, we say, okay, for this period I have these different media available. Which ones am I taking and at what bit rate? Because in each of these adaptation sets we see there's a 5 megabit per second version and a 2 megabit per second version. The media data, by the way, doesn't have to be here. These can all be pointers. In fact, the pointer's about the end. It's just telling us about what's available. So the further breakdown here is showing the example of 2 megabit per second. And for the 2 megabit per second version, the information about that segment is listed here, where we have 15-second chunks and the location where each of them can be obtained. Okay. So the client, having decided that during a particular time interval it wanted the 2 megabit per second version, just works its way through these links to obtain the media segment at the right bit rate. But then when it wants to, it can change to the 500 kilobit per second version or something else. So here's an example. This comes from the same IEEE paper that describes this standard, but it quite nicely illustrates the sort of flexibility that can be obtained. So as you see here, if we look at these numbers in order, from at time segment 1, we're playing the 128 kilobit per second AAC audio in English, while we have the high bitrate 5 megabit per second video. But at some stage maybe there's some network congestion, so the video bitrate drops initially, and then both the video and audio rates drop at point number 3. And then they play on at that low rate for a bit. The network congestion improves, the buffer is starting to increase, so we go up to the higher bit rate at point number 4. But then we can also use this adaptive, or this multi-rate file, multiple version file structure, not just to adapt to network variations, but also for different capabilities. So at point number 5, we've jumped out of the real-time playback and we've gone into the trick mode to rewind past. Maybe we go back through a series of stills, and we start playing at point number 6 at a high rate and in French, right? And just decide to switch over to another language and continue on. So there are lots of reasons why you might navigate around the available streams, and some of them are listed there. So they could include user preferences of language, or jumping into fast forward mode, or whatever. Available resources at the client end. So how much CPU power is available at that time. Maybe we're doing other things on our device, so we need to drop back the bit rate, or a configuration change, such as the full screen. So if we're watching video in a window on our PC, then maybe a low rate is adequate, lower quality is adequate. Then we switch to full screen. So we jump from the 2 megabit per second to the 5 megabit per second version. The buffer status, as I mentioned before, so if the buffer starts to empty, then we think, oh, okay, maybe we better switch to a lower bit rate because we get more time per byte received, right? More play out time per byte received. And if the network becomes congested, then we can adapt to it. Just a bit of a check of understanding. Could we use HTTP adaptive streaming for VoIP? No, because
That's sensitive to delay.
exactly. We must always remember that we're building up this large buffer, even if it doesn't look like it to the client and to the user who's watching the movie. There is this long delay between the time the segment left the server and the time that they actually play it out, as a result of building up this buffer internally. So it's not going to work on conversational applications like VoIP. So it has to have that large receiver buffer, and introduces long delays, and it has to accommodate the TCP retransmission time. So it's not going to work on conversational services in general. VoIP is an example, but also video calling, or FaceTime and Skype. So we're never going to achieve the 100 millisecond end-to-end delay with those sorts of constraints. So as a result, RTP UDP isn't in the bin by any means. It still has this important role for these real-time and conversational services. Could we use HTTP on a live event? Like a sports? No, because
live also sensitive to delay.
yeah. No, well, a fair answer, but I think a complete answer really depends on what we mean by live. I'm not. Pardon?
How long is the delay for?
Yeah, exactly. That's right.
If
And
it's sports, then you cannot.
well done.
So you
Yeah,
can still can delay, like if you like delay 1 minute, it's still okay
yeah.
because it's two different parts of the earth. So it's okay.
Well, it's true, and also
It depends on the encoder. Like if you have 1 minute delay, then the encoder can predict for.
yeah. I guess that's true. That if we're prepared to tolerate a 1 minute delay, then we can probably allow the encoder to look a bit further ahead. Yeah. But it depends on what we mean by live. So if I see on my display an event that occurred 60 seconds ago, is that live? And it really depends on the application. So if it's first of all, how can we achieve that live delivery when it's client driven? Well, we're encoding in real time. We're generating multiple versions here. That's what the multiple arrows is intended to indicate, and they're being put constantly on this server, and they're just being put on that server a little bit ahead of what's available to the client. So there is a delay, but it depends on the service, as we said. If it was a live music or performance, probably don't care that much, right? If it was a broadcast of a concert, then you would never know probably if it was a minute behind. Live sports, well, that's depends on the passion of the sports viewer, I guess. Probably texting friends about the latest goal scored or something. There could be problems, but there's a bigger problem for sports on which you can bet. In fact, another little story from Telstra was that was their problem as they were moving over to put Big Pond TV services onto adaptive streaming. All the other channels were fine except for the racing channel, because people who bet on horses I waste my money in other ways. But people who bet on horses like to see the horse in the stalls just about to go, and they see the beads of sweat on the jockey or whatever. So they want to place their bet at the last second. So you can't allow, clearly you can't allow the stream to be 10 seconds, 20 seconds, 30 seconds behind real time if it means placing a bet. Okay, so could we use it for broadcast? Because, or what are you thinking?
It depends again.
On the application.
I've got another qualified response, and it depends on what we mean by broadcast, and that's because, from the service point of view, it can look to the clients like broadcast, but from our traditional view of broadcast being pushing the same signal to all clients, it's not doing that. So it's not broadcast in the transmission sense, but if we are encoding and making these streams available to this server, and lots of different clients can access that same content at about the same time, then from the user's point of view, it looks like each client can get access to the same content at approximately the same time. So that sounds like broadcasting. It's just that we deliver this over a content delivery network. We talked about content delivery network. Yeah. Sorry. So we make whatever savings we can in the core network, but this this local server would contain the.
Each server.
Pardon?
There is each server in the terms of CDN.
I still didn't hear.
In terms of CDN, there is the each server.
Yeah, that's right. Yeah, the edge server. So the edge server has these recently encoded files available, or fragments available, and lots of people can access exactly the same content. So even though it's pooled by the client's managing it, it looks like a broadcast service. So what's happening currently in this space? The efforts are to reduce that delay as much as possible, because that just opens it up for more applications. So this is a graphic that tries to provide a bit of perspective of the delay that occurs with different types of service. Interestingly, the comparison is with cable TV. And cable TV already has a 5-second delay. So, it's not as if non-internet, directly broadcast digital video has near zero delay by any means. The number of processors and buffers and so on that they have to go through, and the encoding delays that we've talked about, mean that it's typically about 5 seconds from studio camera to TV screen anyway. And as you can see, for a very short delay, we've got RTP, RTSP, and for a wide range here, we've got these smooth streaming, the HOS, I'm not sure what that is, HDS, maybe that's the Adobe one, HDTV dynamic streaming, and Dash. HLS, which is the Apple one, goes out to a longer delay because they were using those larger chunks, but they have moved or are moving towards Dash anyway.
What about if we have fiber to the home connection? Do we have the same delay?
We've got the same delay, yeah. It's not a propagation delay. Fiber provides more capacity. Oh, I see. Are you saying in terms of reliability or
speed? I mean, delay, speed.
Well, the source of the delay in the network is not the. Hang on. If we replace cables with fiber, we haven't the signal doesn't get there any sooner, right? It's the same. It's the same distance.
The round-trip time can be less.
No. The
Just improve the link.
Yeah, it can be more reliable, but we still propagate at about 2/3 of the speed of light, whether it's over twisted pair or optical fibre. We would have a much higher bit rate available, but the actual propagation time would be reduced. So I suppose it could improve things in the sense that we could potentially dump files or fragments faster into our receiver buffer. Maybe that was where you were going. So we would not have to start at the the lowest bit rate, maybe. But it's not just the fibre, it's all the routers and stuff in between, and they'll be dimensioned. You know, it's not really a technology problem, it's a dimensioning problem. We can build routers that are, have the capacity and have the switching speed and the buffer size sufficient for any switching load. It's just that it's they're very expensive, and if you're only using that capacity for a fraction of the time, then it's they're over-dimensioned. So they tend not to be dimensioned that high. Worth mentioning that the idea behind adaptive streaming is that the client is in charge, right? The client is controlling what's going on. It gets the manifest file, finds out what bit rates are available, and therefore requests them. And so these large chunks of data potentially being pushed through the network, and that'll allow it to adapt to network performance, but it might not be the rate at which the network provider wants you to have, right? Particularly in, say, a mobile network, where a Telstra or Optus or Vodafone might want to manage the bit rate that's on its network, and it can do that because, unless it's encrypted, I suppose, they can introduce boxes in the middle that intercept the communication between the two ends and actually modify the manifest file. So if the manifest file from here says that there are video bit rates available at 500 kilobits per second, 1 megabit per second, 2 megabit per second, 5 megabit per second, by the time so this client device requests the manifest file, comes along through the network, gets diverted through here, and this one just deletes the 5 megabit per second version. Just says you can have 500, 1 or 2 megabits per second.
Transport buffer, control the transport buffer, control right.
No, this is the network provider just removing that possibility. You don't even see the 5 megabit per second version. So the client continues to control the download. It continues to request the chunks, but it doesn't know that there's a 5 megabit per second version available, so it never requested. So that's the network provider's way of controlling the bit rate that's carried on its network. Okay, so there's just one very small topic that I wanted to finish off with while we're talking about multimedia and the internet, and that's just the existence and support of multimedia in browsers, just because there have been some developments over the last few years. I suppose it is a few years now. And that is that traditionally, before HTML5 actually, video and audio had to be supported by plugins in browsers, and so you're old enough to remember that every time you went to play a video, then it would tell you that your Flash player is out of date, and you'd have to go and update it. And so the Flash or Silverlight only worked as plugins. So it meant that in the HTML code, to include video in an HTML page, there have to be a reference to an external application, Shockwave Flash or Silverlight, with some information that would allow those to run. And then, as I say, then you'd have to keep maintaining those players separately or independently. But plugins have to be installed and they have to be updated, and it was always frustrating because, as I say, it seemed like every time you went to play a video it would tell you that you needed to update Flash. And a lot of people, particularly in the sort of open source internet community, get nervous when there's increasing dependence on proprietary software from specific companies. So no one liked being dependent on Adobe for Flash, for instance, even though I don't think they were an evil company. They didn't seem to be restricting anything people could do with it, but there was this dependency on a particular company and the patents that they held, I suppose. And so there was this big move when the latest version of HTML came out to actually embed video and audio as within the browser. So as a result now, you can call directly that a particular video component comes in a couple of different video formats and play them directly inside the browser. There's been a bit of controversy about which formats are actually supported. As far as I know, and it might have been updated recently, but as far as I know, the H.264 is supported, and I presume there are moves towards H.265. I just wasn't able to find something when I did a quick search the other day. WebM is the Google open source version of the coder, which we talked about briefly. And Theora is a very early open source, by today's standards, very inefficient coder. We didn't even bother talking about it. It's almost like H.261. It's got very limited capability, but the thing is that it's open source, and so some people like it. Very open source and simple. And there is a similar range of audio formats, from just WAV files, which are PCM, Vorbis. I don't think we talked about this one either, but it's an open source audio coding system, and you're familiar with MP3 and AAC, of course. HTML continues to evolve. It's now supporting adaptive streaming, presumably with Dash, and DRM, digital rights management, is coming. I don't think that's available yet either. So, with a new record, 7 minutes before 8, that's all I wanted to cover tonight. So I think we've done well to get through all of that. Remember, we've only got 2 lectures left, and the project is, of course, due Friday, so please.
So, what about if the project includes something from the 2 lectures, next lecture? We don't know.
It's not a problem though, you haven't seen it yet, so that's all right. So please submit it by Thursday, so nothing will go wrong at the last minute. Sorry? The deadline is Friday, but if you leave it till Friday at 11:58, you know what's going to happen. Thanks guys, I'll see you next week. Look, I'm not concerned about us going over a little bit. I'm concerned if it gets to 4 or 4.5 or something.
Hey, I have seen yesterday that I was working on that latest application, and I know that some technology things have to be implemented to that. So I'm working on the latest augmented display.
Augmented reality.
Yeah. So I'm working on the current displays technology that we have.
Oh yeah.
Is it okay, right?
Yeah, sounds good. Yeah. If you want to send me a draft soon, I'll have a look at it.
Yeah, I will go. I will send it to you by Friday morning.
Right, I can't guarantee when I'll get to it, though, that's all.
Okay. So but the final project I will send you by Friday morning. So maybe the draft I will send it to you.
Oh, okay, yeah, that's all right. Yeah, no, you don't send it to me. There's a link on Moodle on the LMS to upload the file when you submit it. Yeah. So don't email it to me. The file.
Fine.
Okay.
And I got some 2-3 latest papers of IEEE which are implementing those the latest display technology. So just going through those 2-3 papers, and I'm collecting these ideas and putting them in.
Good. Sounds good. Okay. Right. See you next week.
So you are waiting now.
Yep. I promise. Yeah, I'll do it. Okay. See you.
So for you again.
Yeah.
I just have a question. Do we need to submit this form?
No, I used to ask for that, but now when you go through when you use the LMS link
Yeah.
submit, it asks you to agree to all that anyway. So
Also, I don't need this one.
I don't
So I just submit that
yeah,
version.
yeah.
Oh, okay.
If you've already created the file, then it's all right. Doesn't matter. But,
Oh, okay.
yeah.
I have that version if you like.
Oh, anyway, gee, you guys are
What
diligent.
conversion?
Yeah, yeah.
Okay. We can throw this one.
Yeah, if you've already got it, it's fine, but you don't really need it because,
Okay.
as I say, I'm pretty sure that it asks you to, it says something like, by submitting this document, you are agreeing to this,
Yeah.
blah, 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 blah. So it serves the same purpose.
Check that out.
Yeah.
Yeah.
Also, another question maybe silly.
No, no.
For the word count, does
Yeah.
it including the executive summary or no?
Well, technically yes, but
Technically yes.
yeah, but,
Okay.
but if you're only a little bit over, I'm not fast. It's,
Okay. I'm not over.
good.
Yeah, also, also, is this my table? Is it a number system is okay for you?
Yeah, that's what I wanted. This is sort of hierarchical. Yeah.
Yeah. Okay. All right. Right. So,
Because I'm trying to access technology about this
Oh, okay. Facial recognition. Yep.
and deep learning is now is the hottest technology. But related to deep learning, there's actually a lot of relevant technology. So So I'm wondering, is it better I access few different technology, or I just focus on one special one is better? And after that, I will discuss about that. Maybe.
Ordinarily, I'd probably say, well, I'd probably give you the choice, but I think once you start getting into deep learning, it's fast. Yeah, and you'll rapidly get away from multimedia and into all sorts of areas. So, yeah, maybe something more specific. Okay.
Question because down here about this one. Can you explain maybe to me again? Because I think the stuff I'm missing is I don't know what I'm missing.
Well, it's just you say that something is more efficient.
Yeah,
It's
more
just
efficient and
more efficient.
something
than
is
what?
reduced. Is it therefore is it the bits to translate because you can use this one to predict this one therefore.
Well, yeah. I'm sorry, I'm not quite sure what you're asking.
Can you just explain this again?
Okay. Yeah.
Yes.
Just there. So, remember that there were those different modes that were available to predict pixels in one block based on what other information had already been encoded, and so and it was based on straight lines effectively. So if there was an edge of some object, then when you're processing this block, you would analyze it, compare it with previous blocks, and say, oh, this has a correlation in that particular direction. And so that would correspond to one of those modes, one of those 0 to 9 or 0 to 8, or whatever they were numbered in HTC. And so so you get that side information along with when you're encoding this block of pixels, and just having that one mode would allow you to look up all the prediction algorithms that tell you that this pixel is based on a prediction from this pixel, this one, or something.
Surrounding
pixels. Yeah, whatever. Neighbouring pixels that are already available to you because they've been encoded and displayed. And then a different mode would mean that the dominant correlation might be in a different direction, and so the prediction algorithm for that pixel would be based on this pixel and this pixel. Right?
So what is the advantage?
The advantage is that if you predict, as with any prediction system, if you predict that signal, then you don't have to encode that part of the signal. But that you've got to send this mode, but then you've already got
the prediction, and so hopefully the prediction is reasonably accurate, and so the size of the signal that's left, the prediction error, is small. So instead of having pixel values here,
pixel or encoding the pixel error.
yeah,
Oh, sorry, prediction error.
yeah. So instead of having to encode that pixel as being value 245, you're encoding it as having prediction error 5. And this one has prediction error -2, and this one has prediction error. Right? So it's a small variance of the signal, and therefore you need few bits to encode it. And maybe if the prediction is good enough, maybe you don't even send the prediction error at all. And that principle of prediction applies whether you're doing whole frame predictions from an iframe to a
Same
T
principle.
frame. Same principle.
Same principle
Yeah.
and concept.
Yeah, so we used motion compensated prediction to predict all of these macro blocks in a P picture based on data from here.
Picture.
And the reason we do it is that if that we want to essentially reduce the variance of the prediction error signal.
Thank you.
No worries.
Another question is about the project, because I did some simulation and use MATLAB. So I was just wondering where should I put my? Do I need to put my code in the like appendix?
Yeah, totally.
Yeah, in appendix.
Yeah, and don't worry about the word count, obviously.
Yeah, of course. Yeah, of course. Another is in the simulation I use some others part of some others code or some functions in MATLAB. I just want to know how to cite this to a reference because I want to probably use it.
Yeah. Can you document it in the MATLAB? Just say this block of code comes from. Is that easy?
And put it in the appendix, or I just mention this
just
in the
have it in the comments in the MATLAB.
Put it in the MATLAB.
Yeah, put it in the comment. Just in one of the comments in MATLAB. You comment out this, you can just say this block of code or this module comes from this reference. Does that work?
I don't know. It's my first time to.
Yeah. Well, I mean, I'm happy with that. If that's.
Or I need to mention it in the report and the part of the simulation.
If it's appropriate, if it's necessary to explain the discussion, if it was a major part, then you could say, then yeah, it would be appropriate to reference it. But if you just got some generic bit of code from the MATLAB library or something.
Oh, it's not. It's from someone else.
Yeah. So
Yeah.
I commented in the MATLAB and also sounds like I refer to it in the report.
And we need to submit our reports and from the LMS from the Tenerife. So how do I need to send you these codes again, or I just put this in the appendix?
Just put it in the appendix. Yeah.
And also
I don't know what Turnitin will do with it, but it doesn't matter.
Yes, and also the code from someone else may be very, very, very long, but it's just a function.
Okay.
And it can be downloaded from the MATLAB, the website. It's uploaded there.
Yeah.
So I won't put that part in the appendix. I just put what I wrote, what I write in the MATLAB.
All right, that's fine. As long as it's clear.
And I just use his function. And yeah, I always say maybe you can download this function from here, and you need to put this one to the same folder, and you can run this.
Okay, that's fine.
This one.
That's fine. Yeah.
Thank you.
Okay.
So much.
Yep.
Very easy. So here we both lose 2 marks. Is it because we didn't write down? We were using the prediction error to encode in the pixel, right?
No, I mean maybe we
lose
missed
2 marks.
we need to mention the mode and the correlation.
No, I write down a mode. You can use a different
Mm-hmm.
mode to compute the pixel based on the surrounding pixel which has been encoded. But I didn't write down the prediction error using the prediction error to encode the pixel or.
Well, yeah, but this was we can use the surround pixel.
to the next pixel or 7 bit, right? And improve the compression rate.
Yeah, but there's nothing. I mean, that's very generic. It's
okay.
right. It's you could say that there's nothing about the sort of correlation direction or the modes.
Okay.
Or,
so you expect to see we write down the correlation direction and
I mean, I don't expect you to memorize how many modes or anything like that, or which one's which.
Yeah.
But that was. I mean, we're talking about this in particular. So this is very generic. It talks about almost any type of prediction. So I gathered that you knew basically what you were talking about, but you weren't very specific.
So what about if I write down, are we using a prediction error to encoding the pixel? Do we get 2 marks?
No, because that's still very generic.
Oh, okay.
I want you to identify what are the features of this particular technique in the intra-prediction that was used in H.264 and H.265.
Okay.
Right.
So, but my explanation here is also not enough, right? Or
no, it's because it applies in any prediction.
Okay.
Situation.
So.
I mean, if.
So what should I write down more here? Can you give me an example?
Well,
I want to know your style, so it's more better for our example, right?
Yeah. Well, what I was expecting was that you would refer to the fact that we're encoding blocks of pixels, and we're encoding them using some assistance data about the dominant direction of correlation. That would be pretty complete. Yes?
Direction of the
dominant
correlation.
direction.
Dominant.
Dominant. Don't have to use my word.
I know.
Dominant direction of correlation.
Yeah, direction of
because it's directional, right?
Direction of the correlation between the 2 points.
Of correlation. Okay, and then blah blah blah.
And then the rest is fine, I think.
Okay.
Okay. Okay. No worries. Thanks.
Because we got a knowledge, but we
I
didn't
know,
get to that point. What you expect? So
I know, and it worries me a little bit, as it probably worries you.
But you obviously, based on our answer here, we know we have the knowledge.
Yeah,
but
I just wasn't sure.
We didn't write down something what you expect, and so So it is more important by ourselves.
But I need to be confident that you understand that specific question, not just generically about prediction.
Okay.
I hope the exam will be better.
Okay. No, because if we don't know the direction correlation, we wouldn't write down. We're using different mode to predict the pixel.
True. Yeah.
Right. So we have the knowledge, but we don't know. So it's hard. Right.
Okay, we'll see you
Right,
guys.
no problem.
Turn the light up,
Right, I will do it.
Thanks.
我知道。
硬盘那一题其实没有很多。
我也没，我反而对了，我刚才听到答案，我对了。